Okay, the first speaker is Shuai Guo. He will talk about the structure of a higher genus chromo-Witten invariance of the quintic threefold. Okay.
Okay, thanks for the invitation. Sorry for the late because some problem of my network. So my title is the structure of the higher genus chromo-Witten invariance of the quintic threefold. So I will start from the definition of the chromo-Witten invariance. So this problem dates back to a classical inverted problem. So say we consider a special class of Calabi-Yau manifold. So let's see here we have the X5. We denote by the quintic threefold the X5. It is the quintic hypersurface in the four-dimensional projective spaces. So here the P is a degree 5 homogeneous polynomial. So the classical problem is that, say, how many rational curves are there on this quintic threefold for each fixed degree D? So now we know the leading numbers. So this is N0D means the number of rational curves of genus 0 and the degree D are computed. They are the 2,875 and the following numbers. We can see they are very large. And if you use the classical way to compute them, it will be very complicated. So this is a classical inverted problem. We will see later that this problem will also related to our approach to higher genus. So now what we call the modern inverted invariance is the so-called the chromo-Witten invariance. It is defined by the following data. So first we consider the pointed curves. So C is an algebraic curve with some special points. We say they are mark points. And then we consider the modular space of the stable maps. So a stable map is from the pointed curve C with some mark points to some target variety. So here C, because we want this modular space to be compact. So these curves we allow them to have nodes. So the worst singularity will be the nodes. So we call them the nodal curve. We also need this map F to have finite automorphism. So this means that, for example, if the target is a point and we have genus 0, then by the complex analysis, we know that we need at least 3 mark points to make this Riemann sphere have finite automorphism. This automorphism need to fix these mark points. So the chromo-Witten invariants are the integrations against these virtual fundamental classes of this modular space of stable maps. So here, these gamma are some cohomology classes in H star X. So let's see, so gamma I lies in this the cohomology class of X. And the EVs are the evaluation maps from this. So EV is the map from this modular space to X, which maps this stable map F to its image of the mark points, so Fx. So then we can pull back of this common class to this modular space, and we define the chromo-Witten invariance to be the following intersection numbers. And we can consider the generating functions of this chromo-Witten invariance. So here I can give you a very simple example. Say that we can consider, for example, the x is equal to P2. So this is a complex projected plan. And then the gamma I, we can pick them all to be the points. And then the Gromit invariance will becomes what? We can see this will becomes some point class. The G and D. Here D will be the class corresponding to the D multiplied by the line class. And then we can, for some dimensional reason, we can simply compute that this number are non-zero unless this n is equal to 3D minus G plus 1, plus G minus 1. This means that when you consider the 3D minus plus 3D plus G minus 1 points, and this Gromit invariance will gives you the number of genus G degree D curves passing through these 3D plus G minus 1 points. So this will recover the classical enormity invariance. Of course, in general, in this Gromit invariance are not matched with this classical enormity invariance. Okay, so in this talk we just care about the Calabi-Yau threefold. So for the Calabi-Yau threefold case, the string equation told us that when you have an insertion of 1, this 1 means the unit in the h dot x, and then this correlator will be 0 unless this in the genus 0 and the degree 0 and with 3 mark point case. So this means that all Gromit invariants of a Calabi-Yau threefold are determined by this special case. So means we have no insertion and we just consider the integration over 1. To recover all the Gromit invariants, we also need some equation called divisor equation. So anyway, so for the Calabi-Yau threefold case, this is a very special case, and in this case, all the information of the Gromit invariants are just these numbers ng beta. Then for Calabi-Yau threefold, the central problem becomes how to compute this generating function, this fgx, and we just sum over all this effective class beta for each genus G. And once you know this fg, you will know all the information of the Gromit invariants we want to know. And also, I want to remark that this big ng beta, you can use this to recover the inertial invariance. So it can recover the classical. Classical inertial invariance. When the genus and the degree are both small. So as I mentioned here, the classical problem is that how many rational curves are there on the Quintic threefold. So when the genus is 0 and the degree is very small, if I remember correctly, when the degree is less than 7, then you can use those Gromit invariant large ng beta to recover this small ngd. So they are related by some now we call the multi-cover formula. The reason is that you can see from the definition this F is the map. So here the Gromit invariance in the definition, in fact, the modular space is modular space of stable maps. And when you consider the degree, it might comes from the degree of the map or the degree of the image in this target. So then you can have some formula to relate the true degree, and then you can recover those small ngd. So I can give you the relation later. But anyway, you can use this guy to recover some classical invariance. In general, to compute this Gromit invariance, it's a very hard problem. Very, very hard. In fact, until now, we don't have a final solution. But the string series gives us the following remarkable two solutions. So the first one is the mirror symmetry. So in the 1990s, Canellas and his collaborators, they introduced the so-called the mirror symmetry conjecture, which is saying that you can recover this genus zero generating function from some B model. So this B model are the period integral over some mirror manifold X. Check. So this is called the B model. We will introduce some details later. So roughly speaking, you can convert some this computation of the F0. This problem is very hard to some very simple problem, which is just a period integral over this mirror manifold X check. And for the higher genus case, to push the mirror symmetry to higher genus later, the four physicists, Bashasky, Sakoti, Uguri, and Vafa, they introduced the higher genus B model. So they claim that for the genus larger than zero, this generating function Fg can be recursively computed from lower genus generating function and some finite initial condition. They call this finite initial condition the ambiguity. We will say more later. Okay, so now I can explain the genus zero mirror theorem. So they claim that this IQZ, these are just these are just these periods. And these periods, you can simply compute them, and you can use the classical geometry theory. You can prove that they are just the solution of the following Picard-Fuchs equation. And the genus zero mirror formula claims that you can recover this F0Q by simply define some J function. So this JK are this IK quotient by I0 for k is equal to 1, 2, 3. And these J, we see these J are just the functions of small q. So J are function of small q, JK. And you can have some mirror map. So the mirror map is defined by the exponential of I1 over I0, because we see from the definition this I1 starts from log Z. I1 is log Q. So you can simply compute that this big Q will be equal to some small q plus some larger powers. So then this mirror map is invertible. And then you can recover all this. You can recover the whole generating function F0 by using these periods. So this means that you can compute all the genus zero invariance for all degree once. So this is the well-known now we call the classical mirror symmetry, and this is already proved by the Giventhal and Lianliu Yao independently. So now in this talk we will mainly interested in the higher genus case. So for the higher genus case, I just gives you some example here. So this is a genus 2 example. So the BCV's family role is recursively is a algorithm. So it tells us you can compute this higher genus FG recursively by using some lower genus FG. So this Feynman graph tells us the first step in the left hand side. This means the F2, the genus 2 generation function, and on the right hand side, you find all the informations only involve the FG for genus no more than 1. So for example, for this graph here, this guy involves F1, and this guy involves F1, and this edge is just defined by some Sij, and this guy is some genus 0 data. So all these guys are genus 0. So then you can look at all these graphs, and this tells you can compute this F2 by just some combinatorial formulas of this lower genus, and plus some, this guy is some what they call ambiguity. This is just the initial data, what I mentioned. This only involves, so this only involve 3G minus 3 formatting invariance. In fact, this F2 is a polynomial in some rational functions of degree 3G minus 3. This for this 3G minus 3, I mean for the quintic case. And in general, this will be more complicated, but it still involves finite information. And then in following the work of BCOV, Yamaguchi Yao also deduced the following the finite generation property and a set of functional equations. So this, now we know these are equivalent to the BCOV's Feynman rule. So also, so hence this BCOV conjecture also have an alternative form in the literature, in the Yamaguchi Yao's form. So it is equivalent to some finite generation property and some functional equations. Okay. So then, following BCOV, the Yamaguchi Yao and Katz-Klemm-Waffa and then Huang-Ken-Quickenbush, in a series of these subsequent works, these physicists, they gives us a general algorithm for the higher genus FG. So it consists of two parts from the B model and the A model respectively. So for the B model part, now we call them the BCOV exosome. So this consists of three parts. So the first part is the BCOV's Feynman rule, which we have mentioned. This BCOV's Feynman rule is the most important part because it just decreases the information from infinity. So for each G, we need to compute the infinity one, the chromatin ones, now to some finite number. And then they consider the so-called the global mirror symmetry. So the global mirror symmetry here is mainly mentioned in these two parts. For example, they call something called the orbifold regularity or the conifold gap. This means that there is some geometric theory at other points in the global B model. And then this other conjecture theory, in fact, we don't know how exactly what is theory are. Except for the orbifold theory, we already know it should be the so-called, now it's well known as the quantum singularity theory or FGRW theory. But for the conifold point, or in general, there might be other types of singular point. We don't know what is the geometric theory are. And but this physicists, they claim that we can use the property of this geometric theory to give you some constraints and deduce this initial data, this final data to some smaller initial data. And this is all from the B model part. And from A model part, they use something we call the Gupta-Vafa conjecture, which is just related to what we have talked about, the classical innovative geometry. So as I have mentioned, when the genus and the degree are small, this innovative invariant, so this small ng bit are just exactly the classical innovative invariants. But in general, we don't know what exactly they are. There are some results, but there's still many things we don't know. And if we assume they are just simply those classical innovative invariants, then we can apply the so-called Casanova bound. This is the bound which means that when the genus is very large with respect to the degree, then the ng bit will vanish. So for example, this is just something generalized, some well-known fact we know. For example, for the curves for the degree d curves in the complex plane, then we know by Riemann-Roch is genus. When the curve is smooth, the genus will be d plus 1 times should be d minus 1 times d minus 2 over 2. So for example, the degree 1, the degree 2 curves are just rational curves, right? So in general, if we consider this degree d curves in the quintic, we still have some bound. So this is the Casanova bound. And if we just assume this, after this Gupta-Vafa conjecture means that we have this invertible transformation, we transfer those big ng bit to some small ng bit. This transformation are invertible. And we assume these small ng bit are enumerative invariants. Then it should have some degree bound, and this degree bound will give us information and will give us some constraint to those Fg. Okay, now we can see what happens in the quintic threefold case. For the quintic threefold case, those physicists, they have a very concrete analysis, and they say that first the BCOV's Feynman rule, they convert the problem from infinite many Gromit invariants to 3-2 Gromit invariants. And then the orbifold regularity will then fix 3 over 5 initial data. And further, the conifold gap then fix 2G-2 initial data. So this means that by this BCOV's axiom, we deduce from infinity to 2G-2 over 5 initial data. This is this line. So this part we don't know. This is the unknown. And then once we know this part, then we know all the numbers for each genus. And then what the innovative geometry told us? The innovative geometry tells us that there is a bound for each. Well, if you fix degree, then that means if you fix genus, then that means you know some vanishing problem for the degree. So this means we know for each genus, we know that when the degree, let's see, there will be a degree bound. So maybe I should say something, or something like this. Sorry. Let's see. So here this is the bound is say that for a fixed degree, we know the genus larger than its vanishes. So then for each genus there will be a largest degree, right? And then this largest degree will give you some bound here. This will give you some bound here, and this bound will give you constraints that just solve this shadow part which you don't know. But then in the Casanova bound, this curve is for the Casanova bound. This is this Casanova bound intersect with this 2G-3 line at this point. This point is exactly G equals to 51. So this means that this uses all these conjectures that physics gives us, and then you can solve the all the Gromitian invariants up to genus to 51. But then if you want to go further, then even physics they can solve the problem. But anyway, BCOV's Feynman rule will still allow us to convert the problem to a finite rule. Okay, so this is the best result, even conjectures to us. And using these conjectures, the physics compute all these leading Upper-Coma buffer invariants. So you can see these invariants are integers, are all integers. Okay, now I want to introduce the mathematical solutions to these physics conjectures. So this is a very hard problem to you can see I already introduced many conjectures, and even physics they use many tools to solve this problem. Now to solve all these physical conjectures, it will be a very hard problem. So fortunately, we can say something about, at least for the quintic case, we already have many things to say. So for the quintic threefold case, so at least this picture can be general further for general Cargill threefold, but the following would not be. So at least in this page, the result should be for more general Cargill threefold. So we found that the BCOV's Feynman graph sum, in fact, it can be realized as a geometric quantization of the symmetric transformation, some symmetric transformation P in a four-dimensional symmetric vector space. So what is P? This P is exactly this propagators appear in the BCOV's Feynman rule, because this Feynman rule we want to compute some higher genus Fg. Then in the right hand side you will need to put some Sij on these edges, and then you put some Fg on this curve, some lower genus curve. So you can see this so they call this Sij propagators, and these propagators will appear everywhere. And this graph sum, in fact, we found it is just exactly the classical geometric quantization can be defined from the classical geometric quantization. So we can write down the formula. So it means that we can define this quantization of this E to F. So F is the generating function we already defined with some simple modification. And this will be a function of some coordinates we call X. And this will equal to the geometry quantization say that the quantization operator is defined by some integration over the symplectic vector space. So 4-dimensional is R4. So we just give some suitable inner product to make it symplectic. And the integrations will be something like this. And plus this step, dx dp. So this Q is some quadratic form. And this Q is defined from this propagator matrix, this symplectic transformation P. So you can use this. Oh, sorry, this big P is not this coordinate small p. This P you can use this P to define this Q. So this is 4-dimensional, means we have this X is X1, X2, and P1, P2. So this is a very simple classical result. You just do some simple computation, you can find this is exactly BCO with Feynman graph. So, and then the next step is that we found this symplectic transformation, you can lift it to a larger, the symplectic transformation in a larger dimensional symplectic vector space, a 12-dimensional. So you mean that we can lift this P to some, maybe we should call it P tilde, and such that this P tilde restrict to this R4 is exactly this P. And also we found that after this lifting, we need to simply modify this F1. And after this two operation, then we found this quantization, the graph sum given by this quantization is exactly equivalent to the quantization given by this way. And this guy is exactly, you can recover it from the Given-Tose quantization. So Given-Tose quantization is a quantization in the infinite dimensional symmetric vector space. And you can further lift this P tilde to some symplectic transformation in this infinite vector space. We call it PZ because it will depend on Z. And then we will find that the quantization, the Given-Tose quantization exactly will recover this geometric quantization in this case. Okay, now then the BCOV's Feynman rule, to solve this BCOV's Feynman rule, the problem becomes that we consider the mass potential defined by the quantization acting by this R matrix action. This means just the R matrix action we usually means the Given-Tose quantization. So here we define this mass potential by just the quantization action on this FG. And the BCOV's Feynman rule means that this guy is a degree 3g minus 3 polynomial in some rational functions in Q. And our aim is that to find this, what we call this propagator matrix P from some suitable localization of some suitable geometric theory. And then we found that the theory of n mixed spin P field divided by the Chang and myself and Li Liu might be a right answer. So to To give this, in the following, I will just give a very brief explanation of our proof to the BCOV's Feynman rule. So the first is that we want to explain that the NMSP module has, when you do the localization of this MSP module, you will find it has three, the fixed loss set will have three label, which correspond to the quintic threefold. We label it by 0. The 1 is, we mean it is a point. And then we have labeled by infinity means it is some singularity theory. So the singularity theory is what we don't want it because it's complicated, as complicated as the quintic theory. So the first step is that we prove the, if we define some theory called 0-1 theory, this 0-1 theory is just defined by we just sum the localization graphs only supported on the 0 and 1 point, labeled by 0 and 1, those points. And then we found this 0-1 theory will has exactly the same polynomiality with this total NMSP theory. So then we can just think that this 0-1 theory as a module which has the same good property as the NMSP module space. And then also the 0-1 theory has the advantage is that it can be considered as what we call the cohomological field theory. And this cohomological field theory is defined by the R matrix action on this quintic theory and the Gromitian theory of some points we call endpoint, because here n means that we add many field called there are n field, and we hope to make this n very large. Okay, sorry, this series too complicated, but I just want to very roughly gives this picture. So the picture is in fact also related to the original BCOV's theory. So we know that the BCOV's Feynman rule is deduced by some Feynman integral over an infinite dimensional space. So this is not mathematically well defined. That's why we call they are conjectures. And they use this computation, not mathematically rigorous, to deduce the Feynman rule. So now to make this way to approach infinity mathematical rigorous, we found some algebraic way. The way is that so by this localization, we get some R matrix. Maybe let's draw some picture. We got some very large R matrix. We call this R. This matrix is the quintic threefold is the 4-dimension. It has state space of 4-dimension. And then we have n points. So then n points will give us n. So the matrix is a square matrix of 4 plus n times 4 plus n. And so what we found, the fact is that when we make this n very large, goes to infinity, we found that, so first, this other part, this shadow part, will becomes very simple. This will gives, so roughly speaking, this will only contribute to the ambiguity part. That is the polynomial of degree 3 minus 3 in X. And what is more important is that we found this part. When this n goes infinity, this part will change, but this part will goes to what? Goes to the propagator matrix P. So then we recover this propagator matrix from this given to R matrix that appears in this localization of the 0, 1 theory. And then we can prove the BCOV conjecture, because in last step, we already say that 0, 1 theory is already a polynomial in X of degree no more than G minus 1. And then we prove that this shadow part will gives you the polynomial contribution of degree no more than 3 G minus 3. And then the rest part is just exactly the BCOV's Feynman rules contribution. Okay, this is I just try to give a very rough idea to how to prove this BCOV's Feynman rule. And we found that in even in the original conjecture and also in our approach, we both use something, some way to approach the infinite. And then, as I have mentioned, there are some other parts which deduce the initial condition. And also this BCOV's axiom, they have some equivalent representation. For example, as I mentioned, the Yamaguchi-Yao's functional equation and this finite generation property. And then to solve this part, in the joint work with Yang and Ran, we prove the following equivalence. We prove that all these 3 B models axiom, the BCOV's axiom, for this we call extended quintic family, because this contains the quintic as a special point. And then we prove that this is equivalent to the following property for the formal quintic. The formal quintic is defined by some theory which is much simpler than the quintic theory. This is so roughly speaking, this is an equivalent theory. You can do localization formula, and in principle, you can compute all these invariants. Not like the quintic, even for higher genes, we cannot even compute them, even for the physics. And then we found that this extended quintic family is related to the formal quintic if we prove the following 3, in fact, 4 property. So first, the finite generation under the holomorphic norm equation is just the same holds for the formal quintic theory, also hold for the extended quintic family. This is because we will see later that this construction preserves this holomorphic norm equation. And also this, what we call this orbital regularity, in this case, in fact, we can prove something more, something better. This is the so-called Langdon-Ginsburg-Harbiel correspondence, meaning that we can really prove that this geometric theory has the correspondence with the so-called quantum singularity theory. Anyway, this will gives us, this will fix 3 minus 3 over 5 data, as we mentioned. And for the last part is very interesting because we need something more. So we need not only the conifold gap for the formal quintic theory, we also need the regularity for the formal quintic theory. And if we prove all of them, then as a corollary, we will prove the mirror formula for some lower genus. And because now for this part, we can only prove this for the genus lower than 5. So that's why we only prove the mirror formula for genus lower than 5. Okay, so the picture is like this. So first is that by the idea of Felix Yanda, so it gives us a localization formula of the log gauge linear signal model moduli. And this formula allows us to write down this quintic theory in terms of the bipartite graph sum of some twisted theory. So we write down quintic theory as a graph sum of twisted theory, and twisted theory is computable. And of course, there are some details here. For example, this twisted theory is not the formal quintic theory we want, but after some argument, we can convert those twisted theory to the formal quintic theory. And then, as I have mentioned, this graph sum will preserve the holomorphic norm equation. So no matter which, so there we have 2 points, which one is 0 and the other is infinity. So here this 0 theory is the twisted theory. And the infinity part is something they call the effective theory. This is unknown. This is totally unknown. But anyway, we just need their existence. We can't compute them. So the result in this page claims that no matter what the effective theory are, they are so the effective theory we can define some effect constant. No matter what these effective constants are, this result will always hold. That's why we prove this for the extended quintic family. So we just know there are some constants that make the graph sum is equal to the true quintic theory. And this bipartite graph sum, we can do some stabilization of them, and then we also can have some other type of generalization of this R-matrix action as given host R-matrix action over this infinite dimensional state space. But the advantage is that the graph sum is always finite. That makes this graph sum computable, because we can do some argument to say that this for each genus there are some bound for this effective theory, such that there only finite effective theory exists in each case. And then the last interesting, we mentioned this conifold gap and the regularity, is that the conifold gap is in fact saying that, so for example, for Gen 2 case, so that means this Fg is equal to all these guys summed together. And the conifold gap means that this Fg, when you expand it at some other special point, this will equal to, so if we denote by delta the conifold coordinate, it will look like something like delta 2g minus 2. There's some constant, I don't remember, it's something related to the Bernoulli number, then plus some regular part of this delta. This is what we call the conifold gap. And this equivalence we prove is that we found, at least for lower genus, we found this conifold gap is equivalent to say that the leading term. So this is just some, how to say, experiment result. We experiment to genus 5. This is correct. That all this gap part is contributed from the contributed by this leading graph. So this guy will also be equal to delta 2g minus 2 over something like this, and all the other contributions are regular. That's why we say that this BCOV's axiom, the last part is the conifold gap, is equivalent to the conifold gap and the conifold regularity. Regularity means all these other graphs, they are some twisted theory with some special insertions. In fact, this structure is very amazing for me because I even don't expect this result. The reason is, so here, this picture is that we write down this quintic theory in terms of some formal theory summation. But if you want to think about some general Calabi-Yau threefold, then you will find that the formal theory even not exist in general. So, sorry, I didn't told you the definition of the formal theory, but it's some very special equivalence theory. And if you consider some, for example, hypersurface in the weighted project space, then the formal theory will not exist. That's why this result makes me think it is very amazing, because this should not hold in general, but for quintic it appear, and for other one parameter models we also check that it appear. I mean, for the non-orbifold case, and they also have some behaviors like this. But we can prove it's general, so because the twisted theory is computable, we can check genus by genus that this is true. That's why we can check up to genus 5's conjecture is true. Anyway, for this BCOV's axiom, so using this correspondence, we can prove this first part, the second part, and the third part up to genus 5. And we are very interested to know why this holds for general, and we hope to have some progress in the future. Okay, so this is all the story for the quintic that I know. So thank you.
Okay. Thank you. Are there any question and comment?
Hello?
Yeah.
How to see BCOV Feynman rule for higher genus?
Yeah. Sorry.
How to see the Feynman rule?
Oh, so Feynman rule means that. Okay, let's see here. So the Feynman rule, the Feynman graph sum means this graph sum. The rule means that this F2 is you can. So let me explain this more. So first you see that there is a minus sign. So usually maybe we should write this. This is some leading graph. So usually we should write something like this plus some lower genus graph. For example, you can write down this. And more, you can write this as this is called the Feynman graph sum. And then the Feynman rule means that this sum is equal to what they call F2T. The rule is saying that this guy is a polynomial in X of some degree, have some degree bound. Have some degree bound. Yeah, this is the rule. That's why they say this Feynman rule.
Equations comes out so naturally. the coefficients, how to see that?
You mean the coefficient of this F2T? We can't compute it directly, but we can only do that. We can compute the lower genus sperm-wetting environment because this F2 is equal to some, if you remember, it is equal to some graph sum of some lower genus sperm-wetting environments. And then you can use this guy to recover this the coefficient of this polynomial, because this polynomial has only finite coefficient. So you can compute finite small degree sperm-wetting environments to recover it. Of course, a physical way is, as I mentioned, they use all this global mirror symmetry and other data to fix that. So that's the most hard part after BCOV span rule. So the hard part is the finite number, how to compute them. So for the quintic case, as I draw this picture, they have many constraints, and they use these constraints to say that up to genus 51, those constraints are enough. But for larger genus, those constraints are not enough.
Okay, if no question, let us thanks to speaker again. We will restart at GMT 8:15. Okay.
Okay. Let me stop.